there are some problems when it comes to remote sensing of trace gases in the atmosphere. It is not only the trace gases in the atmosphere that affects the reflectance retrieved by the satellite sensor. So therefore, there are a lot of challenges when we need to convert this measured reflectance into the actual tropospheric trace gas concentration product. For example, some part of the radiation hits the ground surface and is reflected back to the atmosphere. That ground surface is not a part of the concentrations in the atmosphere, so we have to deal with this issue with the surface. Within the atmosphere, we have aerosols that is floating around. They can also influence the reflectance that is measured with from the satellite. So that's also something that needs to be dealt with. Then we have atmospheric scattering. The reason the sky is blue, that some parts of the incoming solar radiation is scattered, and that's also another part that we need to deal with. The atmosphere does not only have the trace gas, which we are interested in measuring. There are many different trace gases, so we need to consider to remove the concentration of those ones as well. And we are living in the troposphere, and that's why we are interested in what's occurring down in the troposphere, because that's the main part of the atmosphere where, or this is the part of the atmosphere where we are living. Clouds can, of course, also interfere with our measurements. We need to remove all cloudy scenes. And then if the incoming radiation is coming from the sun like this, and the satellite is up here, and the reflected is going this way, then we have a completely different length of the path within the atmosphere compared to if the sun is here and the satellite is here. So we need to consider the solar and viewing geometry at the point in time when we're taking up the measurement. And then, as mentioned, it's not an actual measurement. We are creating a model to convert this reflectance into the product, and therefore we need to look at consider the accuracy of these models as well. So the first problem to deal with is what to do with the ground surface reflectance. And there are different methods to remove the influence of the ground reflection. The absolutely most common one, and which is most often used in the remote sensing of atmospheric trace gases, is to use ultraviolet and short visible wavelengths. The reason for this is that when ultraviolet radiation hits the ground surface, almost all of it is absorbed, and thereby the amount that is reflected back to the satellite sensor can be assumed to derive from the atmosphere and not from the ground surface. Another method is to use regression modeling, where it's actually the opposite for the near infrared. It's not affected by what's going on in the atmosphere and only affected by what's going on the ground surface. So thereby, by using a regression model between the near infrared and the wavelength which we are interested in, we can remove what's going on the ground. A third method is to use the angular signatures. That is how the radiation is reflected from the ground in different angles, and this is independent on the different wavelengths. So by looking at the angular signatures of the wavelength which we are interested in and another wavelength, we can remove the impact of the ground surface. And the final method is to use the near minimum over time, which is then assumed to be the one that is most affected by the by the atmosphere. But most importantly is the first method to use the short wavelengths, because almost all of it is absorbed by the ground, and thereby we can assume that what we see is coming from the atmosphere. So we have now decided that we are going to study the ultraviolet and the short visible wavelengths of the reflected radiation that comes to the satellite sensor. And we're now going through the process of how to convert these wavelengths of reflected radiation into a final trace gas product. So we start with having incoming and reflected radiance. And then we will use a model which is called Beer's law, which relates the amount of radiation that is absorbed with the concentration of basically anything. This is just a law, but in our case then, the concentration of an atmospheric air pollution, a trace gas. But as mentioned before, we still have some other challenges which we need to deal with. We have scattering within the atmosphere, both from molecules and from aerosols. So we need to remove the impact of this. And then in the atmosphere, there are more trace gases than just the trace gas which we are interested in, which in this case will be nitrogen dioxide. So therefore, we need to remove the impact of all other trace gases. Also, as mentioned before, we are mainly interested in what's occurring in the part of the atmosphere where there is life, the troposphere. So we need to remove all parts which is above the troposphere. And then we also need to filter out all the cloudy images, since of course they can also affect our measurements. And we also need to consider the impact if the sun is coming from this direction and the satellite is coming in this direction. The light path will be much longer, and thereby more of the radiation will be absorbed, since it's going through a longer path in the atmosphere compared to if it's coming from above. So we need to correct for this light path as well. But once we have done all these steps, we have managed to get a final trace gas product. And now I will go through each and one of these steps, how to come from this incoming and reflected radiance into this final trace gas product. So we'd start with incoming radiation from the sun and reflected radiation back to space from Earth. And this amount that is coming in is heavily dependent on wavelength, so that more radiation is coming in, less radiation is coming in these shortwave wavelengths compared to the near infrared and the visible wavelengths, and less is also coming in this ultraviolet wavelengths. Same thing with the amount that is reflected back to space from Earth. It's also depending on the wavelength, so that more is reflected back at the visible and the near infrared compared to the shortwave infrareds and the ultraviolets. And these dip here, they are caused by that water is absorbing much in these wavelengths here. So thereby we can use this information on the reflected radiance on things that is occurring on the Earth's surface. Like, and in a laboratory, it has been shown that, for example, if you would be interested in studying the sulfur dioxide, you can study these wavelengths here between 315 and 327 nanometers, because the sulfur dioxide is absorbing a lot of the radiation in these wavelengths here. And in our case, we are going through the retrieval process of the nitrogen dioxide now. So we are interested in what's going on in these wavelengths here, 425 to 450 nanometers. So what we therefore do is we put a sensor on a satellite which measure these wavelengths between 425 and 450, and we measure the reflected radiation in each wavelength between 425 and 450. So what we get back then is information on how much radiation that is coming in from the sun in each wavelength and how much radiation that is reflected back from the Earth's surface in each of these wavelengths. And then we can use this information to estimate how much that is absorbed by the Earth's surface and try to relate this to the concentration of the nitrogen dioxides. So from our satellite, we now have measurements of incoming radiation in the different wavelengths and reflected radiation back from the Earth's surface. And then the difference between the two is what is absorbed by the Earth's surface. And in order to relate this to the concentration of the trace gas that we are interested in, we use something that is called the Beer's law. And Beer's law relates the amount of radiation that is transmitted through the atmosphere to the amount that is incoming. So here we have the incoming radiation from the sun, and then the amount that is transmitted decreases depending on how efficient the gas is in absorbing the radiation and the concentration of the gas. So this slant column density is the same thing as the concentration of the gas. So as an example, pretend that this is the sun that shines into the atmosphere. If we then pretend that at unit 1 here, or 1 below, we can see that the amount that goes through is substantially less than the amount that is coming in. So the amount that is coming in, let's say that that's 1000 watts per square meter. And then when it has passed 1 unit of trace gas concentration, a certain amount have been absorbed. So if you see here, much less is going through. So a lot of radiation has been absorbed. If we don't go further down into 2 units below, we can see that even more is absorbed. So, but the further down we go down here, the less the difference there is. So, and that's what Beer's law tells us, that there is an exponential decay in the amount of radiation that is absorbed by the increase in the concentration of the tropospheric trace gas. Okay, so let's make a little experiment here. What you can see here is my desk lamp. Let's pretend that this is the sun. Next thing you can see here, a glass of water. Let's pretend that this is the atmosphere. This is the bad guy. This is the polluter, the one that is emitting nitrogen dioxide into the atmosphere. So, okay. So if we start first, we have the incoming radiation going through a clean atmosphere. 1000 watts of solar radiation is going straight through the atmosphere. And as you can see, it's very clean and nothing is absorbed. So we, at 0, we put 1 point there at 1000. So what happens now? When the bad guy comes and emits some nitrogen dioxide into the atmosphere. So you can see now that it's quite a big difference between having a completely clean atmosphere and an atmosphere with 1 unit of nitrogen dioxide. Substantially less radiation is going through. So we put of the 1 unit, we put it down here. Then the bad guy emits another unit of nitrogen dioxide. And you can see that now even substantially less is going through. It's a pretty dirty one. So now we have 2 units, we are going down here. And then the factory emits even more nitrogen dioxide. And you can see now, okay, it's even less going through, but it was not as big difference as between that one to that one, and from that one to that one, as it was between 2 and 3. So let's put it here, for example. And with even more being emitted, now you can see that, okay, it's less going through, but it's not as huge difference again. And the more we emit now, the less of a difference it makes. We don't see very much difference when putting even more through here in here now. So you can see that when there is already high concentrations, there is less and less difference. And that is why the amount that is transmitted has like this exponential relationship with the concentration in the nitrogen dioxide, as shown by Beer's law. So what we started out with was incoming radiation from the sun in these different wavelengths between 425 and 450 nanometers. That's the same thing as here, the incoming radiation. And then we have the reflected radiation from the Earth's surface. And that's this part here, which is the transmitted radiation that is going through the atmosphere. So by simply taking the incoming and divide the transmitted with the incoming, we convert this to the reflectance. You all know what the reflectance is. It's simply the reflected radiation divided by the incoming radiation. So we have a negative exponential relationship between the concentration of the gas and the reflectance that we measure. Just like we showed in our little experiment before, there is at low concentrations, there is a high reflectance, and at a high concentration, there is a low reflectance. And then, by taking the logarithm of an exponential relationship, we convert it to become linear. So we just, by taking the logarithm of our measured reflectance, we get a linear relationship to the concentration of the gas. And this is called the optical depth. But don't worry, the optical depth is just exactly the same thing as the logarithm of the reflectance. So just to show you what you actually do when you take this logarithm is, as you remember from our measurements, we have this exponential decaying relationship between transmitted radiation and the concentration. And when you do the logarithmic, you convert this to logarithmic, all you do is that instead of like before, each step here was 1 watt of square meter of radiation that is going through the atmosphere. You convert this to that each step is instead on the base of 10. So 1 step here means 10 watts. To the next step, it's on the base of 10, so it will mean that the next step it goes into up to 100, and then for another step after that, it's from 100 to 1000. So what you do here is you simply convert an exponential relationship into a linear relationship. So that's what you do when you do we take the logarithm of this relationship, which we have shown. So what we next need to do is to relate our measurements of the optical depth, or the logarithm of the transmitted divided by the incoming, with the actual concentrations of the trace gas. And what we can start with to do is go to a laboratory. We have a certain amount of air, and we put in a certain concentration of nitrogen dioxide. We put in incoming radiation, and we put a sensor on the back of this part of this air, and measure the transmitted radiation. And then we can do this for all these different wavelengths here, between 300 and 500 nanometers. And then you can see that different wavelengths transmit different amount of radiation. So we can use this information to relate what we are measured to the concentration of the trace gas. So say that we would be interested in measuring the sulfur dioxide. Then we would choose to use a wavelength here just above 300 nanometers, because you can see that there is a large variability between the different wavelengths, and sulfur dioxide is only absorbing in this part of the spectrum. So whereas for the nitrogen dioxide, the trace gas which we are interested in, it's absorbing throughout the entire part of the spectrum. But what we are interested in is to find a part which has a big variability between the different wavelengths. So that's why we here chose to have 425 and 450 nanometers. Because as you can see here in the nitrogen dioxide, it's a big variability between the different wavelengths, and this makes it easy to separate the signal of the nitrogen dioxide compared to other signals. So it's like a fingerprint of the nitrogen dioxide, the measured reflectance in these wavelengths here. Additionally, we don't want too many other trace gases to interfere with our measurements. So that's why we're avoiding, in the case of the nitrogen dioxide, we're avoiding this part, because there we have a lot of other trace gases that is affecting the transmitted radiation. Whereas in this part, it's only ozone and nitrogen dioxide that is affecting. So this is the reason we use these 425 to 450 nanometers for the nitrogen dioxide. Okay, so by now, if there would be no problems whatsoever, we would have a model of how to convert the absorbed radiation to the amount of trace gas that it is in within the atmosphere. However, just like we talked about when we started this second part of this lecture, there are some issues that still needs to be dealt with, because the absorption is not only dependent on this trace gas that we are interested in. There are some other factors affecting the absorption. And one thing is, generally here in class, I brought a question: why is the atmosphere blue? And the reason the atmosphere is blue is because of atmospheric scattering. So if the solar radiation is coming in from here, it contains all different wavelengths of radiation. And the longer wavelengths, they easily go through the atmosphere, whereas shorter wavelengths, that is the blue wavelengths, they tend to interact with the molecules within the atmosphere, or the aerosols for that sake. And then they can bounce off. So when we look up at the sky here, we have the sun there. These sun rays come, and some of the blue waves, they are scattering off and thereby hit our eyes, and we see the atmosphere as blue. And this will also happen to the satellite sensor, of course. So therefore, we need to deal with this problem that some of the reflectance that is measured by the satellite doesn't actually come from the part of the atmosphere which we are interested in. It comes from the atmospheric scattering. And as mentioned, the interaction with the molecules, there is the shorter the wavelength, the higher the risk with interacting with the molecules, because the longer ones, they more easily passes through, whereas the shorter they are, the larger the risk of interacting with these molecules. So if we take our measurements from the satellites and convert them to optical depth, at first the measurements will look like this. So a larger part is measured for these shorter wavelengths, since more is coming in there, and then less is coming in this, the longer the wavelength. And this is caused by this scattering effect. And what one can do then to remove this problem is to simply fit the trend line over the wavelengths, and then we simply remove that trend, because then we will remove all errors that is not dependent on wavelength by wavelength, but by the general trend over the entire part of the spectrum. So by fitting this line and removing it, we remove all these errors. And what is left is the actual fingerprint of the atmosphere. So when we have removed this trend over the wavelengths, we get an absorption spectrum which is completely depending on the absorption for the different wavelengths within our atmosphere, which we are interested in. However, there is still one problem with the scattering effect, which we also need to remove. When some of the light is scattered, say the light is coming here, it hits the molecule, most of it is just bounces off, causing these higher values there. But occasionally, a little part of the energy from the light is given to this molecule, and then it might start to turn like this. If the molecule has several atoms, it starts they can start to swing like this. And when these things happen, some of the energy of the light is given to the molecule before it is scattered off. And when some of the energy of the light is given to the molecule, the light changes the wavelength just a little bit. And so when we have this measurement of the wavelength dependent absorption, we still have a little bit of this problem of the scattering left in our measurement. And this also needs to be removed. And this is called the ring effect. And there are measurements of the ring effect from the atmosphere. So we can easily just remove that by taking these reference values. But what we finally have then is the actual absorption that is occurring within our within the atmosphere which we are interested in. So if we start with the original law, we have the absorption that is caused by the concentration of the trace gas, and then we remove the effect of the molecular scattering, that is the Rayleigh scattering, and we remove the effect of the aerosol scattering, that is the Mie scattering, and this is what we do here when we remove this trend. And then we remove the ring effect. This is what we do here. We remove the ring. And when these things have been removed, what is left is the absorption that is caused by the gases within this atmosphere. Okay, so now we have a measurement of the absorption of radiation by the atmosphere for the wavelength between 425 and 450 nanometers. What we can now do is to fit a polynomial to this measurement that will gives us the concentration of some of these trace gases. And this polynomial is based on laboratory measurements, so that we know that at a certain concentration, this is the polynomial that will be fitted to the nitrogen dioxide, for example. And as you could see on the previous slide, that nitrogen dioxide, it was highly variable, whereas ozone, it's more smooth over these wavelengths. So that is just like what you can see here, based on these laboratory measurements. So that we fit this polynomial, and that gives us the nitrogen dioxide estimate and the concentration of nitrogen dioxide in the atmosphere. Then we fit the polynomial of the ozone, that gives us the estimate of the ozone. And then we also have a polynomial for water. And then by removing ozone and water and redoing it, we get the exact estimate for nitrogen dioxide. Then by removing the nitrogen dioxide and the water, we get an exact estimate of the ozone. And finally, the same thing, by removing the nitrogen dioxide and ozone, we get an exact estimate of water. And then finally, of course, there are always some errors when doing measurements, and that is what is left in the as the final part. So when having the corrected Beer's law, we get the concentration of nitrogen dioxide, the gas that we are interested in, and then the concentration of ozone, that is removed, and we remove the concentration of water, and if there would be other gases, we will remove these as well. Okay, so now we have a measurement of the amount of nitrogen dioxide in the atmosphere, that is in the light path from the sun to the satellite sensor for the entire atmosphere. However, we are living in the troposphere, so we are only interested in what is occurring down here in the troposphere. So we want to remove the concentration measurements from the upper part of the atmosphere. Yeah, and there are some different methods to do this. I will only go through the one which is generally used for the nitrogen dioxide product. And what we didn't do is there are no sources of nitrogen dioxide in the Pacific Ocean. That is the reference sector. So we assume that all measurements of nitrogen dioxide is stratospheric from the Pacific Ocean. And then we can simply remove those measurements from the rest of the world to get what is occurring down here in the troposphere. Another issue we had was clouds. Like always, when it comes to optical remote sensing, we need to consider the problems with clouds. And clouds makes us not see a large part of the troposphere. So, of course, we then need to remove measurements taken up during cloudy conditions. And there are products of cloud cover, such as the Modis cloud cover product. and then we can simply filter out all pixels which have a cloud coverage above a certain threshold, such as, for example, 20% or so. Okay, so now we have come to the final part of the retrieval process of the nitrogen dioxide product. Since what we have gotten so far now, we have a measure of the concentration of the nitrogen dioxide, but we have the measurement along the light path. That is from the sun up to the satellite sensor. And this is then, of course, depending on where in the morning or in the afternoon the sun is located and where along the flight path the satellite sensor is. But when we assign a value to a pixel, a certain pixel, we want the concentration that is straight above this pixel. And this is completely depending on solar and viewing geometry and the if there are aerosols and if there are clouds and the vertical distribution of the trace gases. But there are models which we can use to convert this light path measurement of trace gases into a vertical column measurement. And this is what we generally use. So that was the final uncertainty I mentioned in the beginning, the uncertainty of the models which are used for converting these light measurements into the actual tropospheric trace gas concentration. Okay, finally, to summarize. So we start with sending up a satellite sensor to space. From that, we get incoming and reflected radiance from the Earth's surface. Based on these measurements, we calculate the logarithm of the reflectance for each wavelength, and thereby we get the optical depth, which is linearly related to the concentration of the trace gas. But first, we need to remove the problems with scattering, and this is done by simply fitting a trend over the entire wavelength spectrum. And then we remove this, and what we get is the fingerprint of the absorption of each wavelength between 425 and 450 nanometers. Still, we have the problem with the ring effect. Some of the light is absorbed by the molecules and thereby changing the light a little bit. So we remove the ring effect. And what is left is the actual absorption by this package of air. And then we fit some polynomials to estimate the concentration of the different trace gases. Nitrogen dioxide, the one we are interested in, water, and ozone. And what is left is the errors of the measurement. The one we are interested in is this one, the nitrogen dioxide. So there we have an estimate of the nitrogen dioxide concentration in the entire atmosphere. And next, we need to do is to remove the impact of the concentration in the stratosphere. So what we then do, we take measurements from the Pacific Ocean and remove them from the rest of the world, which will give us the concentrations in only the troposphere. However, we still have the problem with measurements being depending on the geometry of the sun and the satellite sensor. So we need to convert this V into what's going on. What is the actual vertical concentration of the trace gas? So we then use a model of this, converting the V into the vertical, And when applying this model, we get the actual concentration that is straight above each pixels here. And we finally have our product of tropospheric nitrogen dioxide.